Physics, mechanics, let's go over the multiple choice. This first one talks about an object released from rest and it reaches terminal velocity. It reaches terminal velocity at the point where the drag force up, which is usually BV, is equal to mg down. So that, it stopped accelerating and it's reached its maximum velocity under the conditions of free fall. And that's when the magnitude of the gravitational force down and the drag force up are going to be equal. Before it reaches terminal, gravity is bigger and thus it's still accelerating. But at some point, these two forces become equal. Remember, anytime it talks about equilibrium, that is going to be when there is no net force. All right, this is the elevator question, and I've given you all three situations. So this equation describes you in an elevator regardless of what you're doing, whether you're accelerating up, whether you're standing still or moving at constant speed, those would be the same, or whether you're actually accelerating down, which means you would be slowing down while moving up. And so if you think about, if you're going to have a positive acceleration, if this is going to be positive, then the normal force has to be bigger than your weight, right? The elevator has to be pushing more than your weight if you're going to accelerate up. If the elevator is pushing exactly the same as the weight, then you have no acceleration, which means you are either standing still or you are moving up or down with constant velocity. However, in this case, if the normal force is less than your weight, then your acceleration must be negative, and so you are slowing down. And so if you can look at a mass of 50 would be roughly a normal or a weight of 500, a normal force of 400 thus would be less. Okay, so you could either be moving upward and slowing down, or you could be moving down with increasing speed, right? Your acceleration clearly is going to be negative if the normal force is less than your weight. Okay, this is our Atwood machine, and when we release this thing, this guy's going to lose potential, and this guy's going to gain potential, but this is going to lose more than that's going to gain because they're going to change the same height, but M1 is going to be bigger than M2. So overall, the system will lose potential, and where does that loss of potential go? Well, it makes the whole thing move. So you lose some potential, but you do gain some kinetic. Okay, this is showing you like a over time kind of dot graph of what's happening here. And so like the object is going dot, 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 dot. It's going really slow here at a constant speed. Then you can see the dots are separating. And so you're going faster. Then you're going to be slowing down, and then you're going at a constant medium speed. Medium speed because the separation here is bigger than the separation here. The average speed for the whole thing, well, that's just the entire distance divided by the entire time. Remember, average is just that entire interval, delta x over delta t. This graph clearly looks like the velocity, right? Constant velocity, slow, then speeding up, then slowing down, and then at the end moving at a medium speed, which is higher than this constant smaller speed. Okay, constant speed at the beginning, speeding up, slowing down, but then your ending velocity is bigger than your beginning velocity. So this has to be the graph, not this guy. And then the acceleration is exactly what we said. No acceleration. The area under the curve would be that increase of velocity. Then the area below the curve would be that decrease in velocity, and then moving at a constant speed at the very end. This is a collision, right? So we take this piece of clay and we drop it on the turntable, and it wants to know a couple things. Number one, it wants to know the new moment of inertia. Well, the moment of inertia is the sum of the individual moments. And so we just take the disk and we add the point particle, and the point particle is mr squared, where its little r is r over 2, because it tells you right there where it drops it. And so you just add them up. What happens to the rotational speed versus the angular momentum? Again, angular momentum is going to stay the same in collisions, right? There's no net torque on the system, so the L1 would equal L2. However, we've increased our moment of inertia, so we are going to then decrease our omega. Again, this is kind of the definition of conservation of angular momentum, or in this case, I guess, looking at how do you change your spin rate, right? So angular velocity is how fast you're spinning, that's omega. And if you want to change that, well, you have to have an alpha. Well, the only way you get an alpha is if you end up having a torque, right? If there's a net torque on the system, then the system will experience an alpha, and the alpha will either then speed up or slow down your spin rate, which is your omega. Again, if you have a constant omega, you have no net torque on you. This is like a double triple question, right? This is the force of gravity, capital G mm over r squared, and they're messing with the radius, and then they're squaring it, and they're messing with the mass of 3, and then you create that factor of 3 force, and so that planet's got 3 force of Earth, and Earth is just G, so then its acceleration is just 3 force of G. This is a total trick question. This number here, totally irrelevant, right? What matters in gravity is the mass of the 2 planets and the distance you are from the planet's center. And it says you are the same distance, x. You're the same distance from their 2 centers, and that the gravitational force is 0. So that means this guy's pulling you the exact same amount of this guy's pulling you, and you're the same distance from them, so they must be the same mass. They have to be pulling you the same amount. Okay? It has to be. So a little calculus here, right? They give you some velocity equation, and they want to know how far it's moved, right? So we know that that delta x is the accumulation of velocity over time. Velocity is always the same, so we can just integrate. We don't have to worry about the absolute value. But really, if you wanted the distance, you would integrate the absolute value. If you wanted the displacement, which is delta x, then you just integrate velocity. Okay, so it's just a little algebra here. Again, this is a definite integral. Do a little power rule. Evaluate it from 1 to 2, which means plug in 2, subtract plugging 1, and then you got to add some of these stupid fractions. Okay, so we take a ball and we toss it symmetrically. We can talk about the vertical speed slows down. Vertically, velocity is 0 at p, and then vertically it goes back to negative, right? And it's symmetrical. Horizontal speed would be the same the entire time because there's no force on it, so v naught cosine theta would just be the same. But as far as g goes, well, dude, gravity, always just down. So it's exactly down at 9.8 meters per second squared. Gravity doesn't care whether you're moving up or down or right or left. Gravity's going to pull you down at that exact rate. This is just a collision, right? This is you jumping on a sled, and then afterwards, classic collision, which means we conserve momentum. So P1 equals P2, and just kind of plug in the numbers. All right, this says right here, elastic, right? When they tell you it's an elastic equation, they're telling you that, hey, clearly it's a collision, so I can conserve momentum, but I also can conserve energy because I'm told it's elastic. That's the definition of an elastic collision. We know that these guys are some things that we really just should memorize, right? We derived those in class. We talked about the limiting values of why they make sense, but these 2 guys are something that it really would be nice to kind of memorize. Now, a couple of things. You could just look at the answers and say, okay, which one of these conserves momentum and conserves energy? And B would do that. Or if you knew these equations, you could plug in m minus a 2m and get these same values. So probably way faster if you just knew these equations rather than kind of going through the answers and verifying which ones conserve momentum and energy. But this one, B, is going to do both of those things. This is just center mass. Remember, we're going to take each mass and weight it by how far it is away from the origin. So we're going to make our origin at the 2 kilogram thing. That's at the 0 mark of the meter stick. And so the 2 is at a 0, the 3 is at a meter away, and that's a total of 5 mass. And so then we get an average position of 0.6, which is 60 centimeters. Okay, we want positive acceleration. Remember, acceleration is a vector, and so we want where the spring is completely compressed, and that's right here. That's when the spring is going to be flying not flying. That's going to be when it's forced to move in the other direction the fastest, right, in terms of right. This would be fully stretched, and that's when the acceleration would be the biggest negative. At 2 seconds and at 4 seconds, it'd be moving the fastest because kinetic energy and velocity are the maximums at equilibrium, where accelerations and forces and potential energy are maximums at the endpoints. Okay, now we've done this one in class. They love this question. This is a more difficult double, triple question, but it wants to know when the kinetic energy is equal to the potential energy. And really, that means if the potential energy is equal to the kinetic energy, that means the potential energy is half of the full potential energy. Because if it's got 1/2 Ka squared and it's got all of it, well, what do you have to do to 1/2 Ka squared to make it half? Because if you make it half, then where'd the other half go? Well, it went to kinetic, which means the kinetic and potential are equal at that moment. And it's one of those things where it's x squared. If you reduce x by half and square it, you're going to get a fourth. So what do you have to do to x to make 1/2 kx squared go down by a factor of a half? Well, you have to reduce x by the square root of 2. Because when you square it, then you'll get a half. Again, 1 over the square root of 2 squared creates that factor of a half, which means that the potential energy went to half. Thus, kinetic energy got half, which means the two things are equal. So you got this guy. All right, if you reduce the amplitude to a over radical 2, you'll actually make it half of what it was. All right, simple harmonic. Remember, simple harmonic, classic is like F equals negative kx. It has to be a linear restoring force. Linear with an x, and it has to be a negative. That's the only way you're going to get that motion that looks like a sine or a cosine curve. This guy, yeah, I get it. It's periodic. It goes boing, 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 fine. So does this. Boing, 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 boing. But it's not simple harmonic. It's not, those are like quadratics, or, I don't even know what this one would be. It'd be nothing really, no real good function. But a mass hanging from in a vertical spring or a horizontal, that's going to go with a restoring force, which does in fact cause simple harmonic motion. This one is very tricky. The tricky part of this one is that the actual surface is frictionless. So there's no friction down here, okay? So if this guy is moving at a constant velocity, and you're pulling it with T2, well, the only force opposing that motion is the friction caused by M on top of 2M. So that must mean that this force and that force are the same, because it says constant velocity. That's really, really important, okay? So if this guy's moving at a constant velocity because of T2 equaling friction, but then if you look just at the top block, well, what's moving the top block to the right? Well, the friction due to 2M. Well, that guy also is moving at a constant speed. So the friction force that way has to equal T1. But that means that T2 equals the friction, but this friction has to equal T1, and so that actually means that those two tensions have to be the same. Again, that doesn't occur often because usually we have friction down here, which changes everything. But with no friction down there, and you get this system moving at a constant velocity, T2 has to equal the friction. Friction 1 has to equal friction 2. Friction 2 then has to equal T1 because M is also moving at a constant velocity, so the two forces have to be balanced. And so we really answered this question as well. And that's really a Newton's third law question, right? The friction caused by M on 2M has to be the same thing that the friction of M, that 2M causes on M. Okay, so this is a little tricky. 1, constant speed, forces must balance, and 2, there's no friction on the bottom. There's only friction between the blocks. Okay, this is in equilibrium, which means the torques and forces have to be the same. So all I did was balance the torque. Definition of torque is force, lever arm, sine of the angle between them. Force, lever arm, sine of the angle between them. And the angle between them is sine of alpha, and so I wrote cosine of theta. And we have discussed that at length in class. The angle between those guys, if I go down here with mg, That top angle is not theta. This angle down there is theta. That's alpha. Sine of alpha is cosine of theta. And when you divide cosine by sine, you do get cotangent. So it's just me taking this equation and solving for the tension. So I just divided. Okay, when you have gears, it's about gear ratio, right? The number of teeth corresponds to the circumference, which corresponds to the radius. And pretty much then, this guy has 3 times the radius, and it's going to be then moving at 1/3 of the speed of the other one. Again, we can derive this by looking at the velocity of the teeth. The teeth themselves have to stay in grooves with each other. So their velocities, V's, have to be the same. But V1 equals omega 1 R1, which equals omega 2 R2. And so when you have a bigger R, you have a smaller omega. And that is something we looked at on an AP free response question. That's typical gear ratio stuff. This is just power rule. Again, this is the definition. They're giving you an equation with theta, and they want stuff about angular acceleration, which is alpha. So just take a derivative of theta and get omega, and then take a derivative of omega and get alpha, and then you can just answer the question. All right, it's just power rule. All right, they trick you with speed here, right? The velocity, right? The velocity actually is just increasing this entire time, but the speed is slowing down to 0 and then speeding up. So just be careful of speed versus velocity. Velocity is a vector, because then up here they're like, hey, what's the acceleration? Well, the acceleration is constant. Look at the slope. The acceleration is a constant positive. You could actually figure out what it is, if you really needed to. It looks like it goes up maybe 5 meters per second in 8, so it looks like maybe a positive 5/8. But again, velocity is increasing the entire time. Speed, it's slowing down and speeding up. So acceleration is some constant positive, and it looks something close to 5/8 meters per second squared. The net displacement, where we're looking at the area under the curve, and it looks like this area and this area are the same. So it's moving to the left, and then it's moving to the right. But as far as what it actually did on that interval, it didn't do anything as far as displacement. Okay, so this piece here gives you some information. It says it starts from rest and it accelerates. So our classic position equation, x equals x naught plus v naught t plus 1/2 at squared, we can get rid of the first 2 terms. And so then the distance we travel is just the 1/2 at squared. So if we use 32 and 4 seconds, we can figure out that we must have been accelerating at 4. Then we can go back and figure out, well, how fast are we moving after 3 seconds, and where are we after 3 seconds? So I went back and just did a 4 meters per second squared acceleration for 3 seconds to move me to 12 meters per second. And then I did the 1/2 at squared again, and I just used 3 seconds to find out it must have been at 18. All right, so this is kind of like looking at this system, right? You're taking 15 newtons and you're just pushing all of that. They're together, right? They're bolted together. It doesn't even know. So if you push 15 newtons and 3 kilograms, you're going to get a 5 meter per second acceleration. But then you're like, oh, let's just now look at block 1. If you look at block 1, what's actually moving block 1? Well, the friction due to the cart. Well, you know that it's accelerating at 5 and it's got a mass of 1 kilogram. It must then have a force of 5 newtons making that happen. And since we know friction is what's making it happen, we can say, oh, well, friction must be 5 if a 1 kilogram block is accelerating at 5. So this is just F equals ma. We know circular motion, right? We know that friction is the one causing the circular motion, and friction can only be so big. So your spin, the radius at which you try to turn your car can only be so small based on the friction. So the path cannot be less than that value. Right? Any tighter than that, you're going to skid away because friction's not going to be big enough. So anytime you're talking about circular motion, right, F equals ma, write the force causing circular motion, and then for A, you're either going to write v squared over r, or occasionally you're going to write omega squared r, and that would just depend on, what the answers are in the multiple choice. And so since this one has the v in it, stick with v squared over r. So this is a collision. There's no external forces, of course. There aren't any. There's never external collisions, external forces during the collision, and so we got momentum. Right? It doesn't matter. Momentum in both x hat, y hat, z hat, and total momentum always conserved. Kinetic energy only if it's elastic, and again, it doesn't say it is. This one, we're taking two different objects and we're dropping them from the same height. Well, if both of them will have the same velocity drop from the same height. So just look at the momentum. Momentum, and there. Their velocity is going to be the same. This one's got 3 times the mass, so this got 3 times momentum, and it's got 3 times the kinetic energy. Their velocities will be the same, so the only thing that's different on these two objects is m. One of them's got a 3m and one of them's got an m, so one of them's going to have 3 times momentum and one of them's going to have 3 times the kinetic energy, right? Momentum and kinetic energy are linearly related to m, so tripling m triples momentum. V is the same. All right, this is just drag forces. Now, normally we graph the velocity graph and we graph the acceleration graph. We know that the velocity drop from rest starts at 0 and then asymptotically approaches terminal velocity. And over here, we start at g and we decay to a 0 acceleration. But they just try to trick you on this one. Instead of graphing velocity, they graph momentum, but instead of graphing acceleration, they graph force. Dude, they're the same. They're just scalar differences, right? If you're graphing velocity, you're just multiplying by a mass, which is the same, I shouldn't say the same, which is a constant. So the momentum graph will look very, very, very similar to the velocity graph. It's just scaled up by a mass. The force graph will look just like the acceleration graph, just multiplied by a mass. So we know what these graphs look like. We know that the acceleration starts at g, decays to 0. The velocity starts at 0 and asymptotically approaches the terminal velocity. So asking you to graph P and F is the same as asking you to graph V and A. Same thing. And the last thing, this is just kind of the definition. This is the potential energy of the big boy version of potential energy. Anytime we start talking about satellites or planets, this is what the graph looks like. And that, honestly, that is just a graph of what a -1 over r looks like. And this is us on the surface of the planet. And this would describe the potential energy as we move further and further away. Okay, as we move away, 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 the potential energy still increases. It just increases asymptotically towards being 0. 0 meaning we're so far away from the planet that we basically can't increase our potential energy more because the force opposing it is basically 0. Okay, 2014.